Imagine accelerating in the most powerful rocket ever built, faster and faster, watching the stars blur past your window. You push the engines harder, burning through impossible amounts of fuel, racing toward that ultimate cosmic speed limit, the speed of light. But here's the crushing reality: we will never make it. Not because we lack the technology or the will, but because the universe itself conspires against us. The faster you go, the heavier you become, time warps around you, and the very fabric of space-time pushes back. Today, we're diving deep into why reaching light speed isn't just difficult, it's fundamentally impossible, and why this cosmic speed limit might actually be the universe's way of protecting us from paradoxes that would tear reality apart. If you're fascinated by the mind-bending physics that govern our universe and want to explore more cosmic mysteries, make sure to subscribe to this channel and hit the thumbs up. Now let's begin. The story of why we can't reach light speed begins with Albert Einstein's Special Relativity, published in 1905. Before Einstein, scientists believed space and time were fixed stages where events played out. But Einstein revealed something far stranger. Space and time are interwoven into a single fabric called space-time, and the speed of light, approximately 300,000 kilometers per second, is the absolute maximum speed at which anything can travel through this fabric. But why is there a speed limit at all? The answer lies in the fundamental structure of reality itself. Light doesn't have mass, which allows it to travel at this maximum speed. Everything with mass, from electrons to elephants to entire planets, must travel slower. And here's where it gets weird. The more energy you pump into accelerating a massive object, the heavier it becomes, requiring even more energy to go faster. It's like trying to push a car that gets heavier with every mile per hour you add. Let me paint you a picture with real numbers. The Parker Solar Probe, humanity's fastest spacecraft, recently broke records by reaching speeds of 195 kilometers per second. That sounds incredibly fast, and it is. You could circle Earth in about 3 minutes at that speed. But compared to light speed, it's crawling at just 0.065% of c. To put this in perspective, if light speed were a marathon, Parker Solar Probe has barely taken its first step. The Large Hadron Collider at CERN provides our best real-world example of approaching light speed. This massive machine accelerates protons to almost 99% the speed of light. At these velocities, the effects of special relativity become dramatic. Those protons become 7,000 times heavier than when at rest. Time dilation means that from the proton's perspective, the 27-kilometer ring appears compressed to just a few meters. This isn't science fiction, it's measured reality, but mass increase is just the beginning of our problems. As you approach light speed, time itself begins to betray you. This isn't metaphorical. Time literally passes at different rates for objects moving at different velocities. GPS satellites orbiting Earth must account for this effect. They're moving fast enough relative to Earth's surface that without relativistic corrections, GPS would accumulate errors of about 10 kilometers per day. Your phone performs Einstein's calculations every time it finds your location. The twin paradox beautifully illustrates this temporal weirdness. Imagine identical twins where one stays on Earth while the other travels to Proxima Centauri at 90% light speed. The journey takes about 4.7 years from Earth's perspective. But for the traveling twin, time passes slower. They experience only about 2 years. They return to find their Earth-bound sibling has aged more than twice as much. This isn't a thought experiment. Particle accelerators confirm this effect millions of times daily with short-lived particles that survive longer when moving at high speeds. Recent experiments have pushed our understanding even further. Scientists at the National Institute of Standards and Technology have measured time dilation at speeds as low as 36 kilometers per hour, about the speed of a car in a school zone. Their atomic clocks are so precise they can detect that your head ages slightly faster than your feet due to the difference in Earth's gravitational field. If such tiny velocities create measurable effects, imagine what happens near light speed. The energy requirements to approach light speed are staggering beyond comprehension. To accelerate a 1 kilogram object, about the weight of a small laptop, to 90% light speed requires energy equivalent to the entire power output of Earth for several minutes. Push to 99% and you need 10 times more. Reach 99.9% and the energy requirements have multiplied by another factor of 10. The pattern is clear. Each step closer to light speed demands exponentially more energy. But here's where physics gets truly mind-bending. As you approach light speed, length contraction kicks in. From your perspective as the traveler, the universe compresses in your direction of motion. That 4.2 light-year journey to Proxima Centauri. At 99.9% light speed, it shrinks to just 60 light days from your perspective. Push even closer to C, and entire galaxies could pass by in what feels like moments. The universe becomes a thin pancake rushing past you. This creates a profound paradox. From Earth's perspective, your journey to another star takes years. From your perspective at near light speed, it might take days. Both perspectives are equally valid. There's no correct reference frame. This relativity of simultaneity means that events that appear simultaneous to one observer happen at different times to another. The universe doesn't have a universal now. Each observer carries their own present moment with them. The Lorentz factor governs all these effects, and it's worth understanding. At low speeds, it's essentially 1, no noticeable effects. At half-light speed, it's about 1.15, time passes 15% slower. At 90% light speed, it jumps to 2.3. At 99% it's 7, at 99.9% it's 22, and as you approach C, it races toward infinity. This mathematical wall is why light speed is unreachable. The electromagnetic force that holds atoms together reveals another barrier to light speed. As objects accelerate, the electromagnetic fields surrounding their particles distort. At everyday speeds, this distortion is negligible, but approaching light speed, these fields compress and intensify in the direction of motion. The SLAC National Accelerator Laboratory has observed this directly. Electrons traveling at near light speed create electromagnetic shock waves that manifest as brilliant blue Cherenkov radiation when passing through certain materials. This field compression has profound consequences. The bonds between atoms in any spacecraft would experience stresses unlike anything in normal physics. Materials that are stable at rest might become unstable at extreme velocities. We're not just fighting energy requirements, we're battling the fundamental forces that hold matter together. Recent experiments with ultra-relativistic heavy ion collisions at Brookhaven National Laboratory show that atomic nuclei literally flatten into pancake shapes at 99.9% of light speed. Let's talk about what happens to light itself from different perspectives. Imagine you're in a spacecraft traveling at 90% light speed and you turn on a flashlight. From your perspective inside the ship, light travels away from the flashlight at exactly C, just as it would if you were standing still. But here's the mind-bender. Observers on Earth also see that same light beam traveling at exactly C, not at your speed, plus C. This invariance of light speed for all observers is what forces all the other weird effects: time dilation, length contraction, and mass increase. The Michelson-Morley experiment in 1887 first hinted at this cosmic conspiracy. Scientists expected to measure Earth's motion through the luminiferous aether by detecting differences in light speed. Instead, they found light traveled at the same speed in all directions, regardless of Earth's motion. This null result was so shocking it took Einstein's genius to explain there is no ether and light speed is constant for everyone. Modern versions of this experiment using laser interferometry confirm this to extraordinary precision. Particle physics provides our most extreme tests of relativistic effects. At Fermilab, muons created in the upper atmosphere are accelerated to 99.94% light speed. Without time dilation, these particles should decay in microseconds, traveling only hundreds of meters. Instead, they survive long enough to reach detectors deep underground, their internal clocks running slow enough to extend their brief lives. We're literally seeing time dilation save particles from death. The cosmic ray paradox offers another window into near-light-speed physics. Ultra-high-energy cosmic rays strike Earth with energies that shouldn't be possible. The GZK cutoff predicts that protons traveling across intergalactic space should lose energy through interactions with the cosmic microwave background. But mass isn't the only thing fighting against light-speed travel. The vacuum of space itself becomes hostile at extreme velocities. What we call empty. Space seethes with quantum fluctuations, virtual particles popping into existence and annihilating in time frames shorter than measurement. At near light speed, these fluctuations blue shift into real, high-energy radiation from the traveler's perspective. The faster you go, the more the vacuum itself bombards you with deadly particles. Recent calculations by physicists at the University of Sydney show that hydrogen atoms floating in interstellar space would impact a near-light-speed spacecraft with the energy of proton beams from the Large Hadron Collider. The gentle rain of particles that barely affects current spacecraft would become a devastating bombardment. Even the cosmic microwave background radiation, that faint afterglow of the Big Bang, would blue shift into deadly gamma rays for travelers approaching light speed. The Unruh effect predicts something even stranger. Accelerating observers should detect a warm bath of particles that stationary observers don't see. The faster you accelerate, the hotter this quantum bath becomes. While this effect is too small to measure with current technology, it suggests that the vacuum itself resists acceleration, adding another layer to the universe's speed limit enforcement. Some physicists speculate this might be connected to inertia itself. Mass might emerge from interactions with quantum fields. Let me share a thought experiment that illustrates the impossibility of light-speed travel. Imagine we build a train that can reach 90% light speed. Now someone runs forward inside the train at 10% light speed relative to the train. Classical physics would say they're moving at light speed relative to the ground, but relativity says no, velocities don't simply add. Instead, they combine through the relativistic velocity addition formula, yielding about 90.4% light speed. No matter how we stack velocities, we never reach c. The energy density of space itself might pose the ultimate barrier. Einstein's E=mc2 tells us mass and energy are interchangeable. As we pump energy into accelerating an object, we're effectively increasing its mass. But beyond a certain point, the energy density might trigger gravitational effects. Some theoretical physicists speculate that attempting to concentrate enough energy to push macroscopic objects to light speed might create black holes instead. The universe might protect its speed limit through gravitational collapse. Tachyons, hypothetical particles that always travel faster than light, illustrate the weirdness of the light-speed barrier from another angle. If such particles existed, they would experience time backward, have imaginary mass, and require infinite energy to slow down to light speed. The same barrier that prevents us from reaching c from below would prevent tachyons from reaching it from above. Light speed isn't just a maximum, it's a cosmic divide between two incompatible realms of physics. The Alcubierre drive, proposed in 1994, seems to offer a loophole. Instead of moving through space faster than light, it would contract space ahead of a spacecraft and expand it behind, carrying the craft faster than light while it remains stationary relative to local space. But recent calculations show this would require exotic matter with negative energy density, something that might not exist. Even if it does, the energy requirements are staggering, equivalent to converting Jupiter's entire mass to energy. Quantum entanglement often gets misrepresented as faster-than-light communication. When entangled particles correlate instantaneously across any distance, it seems like information travels faster than light. But no usable information actually transfers. You can't send messages through entanglement without a classical, light-speed channel to compare results. The universe carefully preserves its speed limit even in the quantum realm, maintaining causality despite allowing non-local correlations. The biological consequences of approaching light speed present another insurmountable barrier. Human bodies evolved in Earth's gentle gravitational field with its specific passage of time. As we accelerate toward light speed, every biological process would be affected by time dilation. From the perspective of Earth observers, a near-light-speed traveler's heartbeat would slow to perhaps 1 beat per hour. Their thoughts would crawl. But from the traveler's perspective, Earth would be racing through time at incredible speed, aging centuries in what feels like years to them. Recent studies on astronauts aboard the International Space Station reveal how even tiny relativistic effects impact human physiology. The ISS orbits at about 7.66 kilometers per second, nowhere near light speed, yet astronauts age slightly slower than people on Earth. Over 6-month missions, they're about 5 milliseconds younger than they would have been. Scale this to near light speeds and the biological implications become staggering. Your body might experience a few years while Earth experiences millennia. The radiation environment at relativistic speeds would be instantly lethal. The cosmic microwave background, harmless at rest, would blue shift into intense gamma radiation. Calculations by researchers at the University of Leicester show that at 99.9% light speed, this ancient light would deliver radiation doses exceeding 10 sieverts per second, enough to cause immediate radiation sickness and death within minutes. No conceivable shielding could protect against this transformed cosmic background. But here's where quantum mechanics adds another layer of impossibility. The Heisenberg uncertainty principle states that we cannot simultaneously know a particle's exact position and momentum. As objects approach light speed, their momentum approaches infinity, which would require their position uncertainty to also approach infinity. In essence, a light-speed object would be everywhere and nowhere simultaneously. The universe's fundamental quantum nature forbids the precise trajectories required for controlled light-speed travel. The vacuum catastrophe in quantum field theory hints at deeper reasons for the speed limit. Empty space should contain infinite energy from quantum fluctuations, yet it doesn't. This suggests unknown physics that might also enforce the light-speed barrier. Recent experiments with the Casimir effect, where closely spaced plates experience force from vacuum fluctuations, confirm that empty space is far from empty. At near light speeds, interactions with this quantum foam might become catastrophic. Gravitational effects add yet another barrier. General relativity shows that energy and momentum curve space-time just like mass does. A spacecraft with near-infinite kinetic energy would create gravitational fields comparable to black holes. Some physicists speculate that attempting to reach light speed might trigger gravitational collapse, creating a black hole instead of achieving faster travel. The universe might protect causality through gravitational catastrophe. Speaking of the challenges of space travel and our cosmic limitations, this connects perfectly to humanity's broader aspirations beyond Earth. If you're curious about whether we'll ever explore other star systems given these fundamental barriers, check out my video, Will We Ever Leave Our Solar System?, where we explore the realistic possibilities and challenges of interstellar travel. The link is in the description below and pinned on the comments. The thermodynamic implications of near-light-speed travel reveal another impossibility. The second law of thermodynamics, entropy always increases, would be severely challenged by light-speed travel. From different reference frames, entropy would appear to increase in different directions. This could lead to paradoxes where cause and effect reverse, breaking the fundamental arrow of time. The universe might forbid light speed to preserve thermodynamic consistency. Recent observations of high-energy astrophysical phenomena provide natural experiments in extreme velocities. Gamma-ray bursts accelerate particles to 99.9% light speed or higher. These cosmic accelerators show us what happens at extreme energies. Particles radiate away energy through synchrotron radiation, creating a natural break that prevents reaching C. The universe has built-in mechanisms that bleed energy from ultra-relativistic particles. The information paradox presents a fundamental barrier. Information cannot travel faster than light without breaking causality. Effects could precede causes, creating grandfather paradoxes. But as objects approach light speed, the information they carry becomes increasingly difficult to decode due to extreme blue and redshifting. At light speed itself, all information would be infinitely compressed or stretched, making communication impossible. The universe protects causality by making light speed travel informationally meaningless. Let's examine what particle accelerators teach us about the light speed barrier. The collisions create quark-gluon plasma, matter so hot it existed only in the first microseconds after the Big Bang. These experiments show that approaching light speed doesn't just require energy, it fundamentally transforms matter itself. The holographic principle suggests space-time might be fundamentally discrete at the Planck scale. If space is pixelated rather than continuous, motion might be inherently limited. Just as a computer screen can only display motion by jumping between pixels, objects might only move by jumping between discrete space-time points. Light speed might represent the maximum rate of these jumps, a cosmic refresh rate that nothing can exceed. Wormholes often get proposed as a way around the light speed barrier. While general relativity allows these space-time shortcuts, they would collapse instantly without exotic matter to prop them open. Recent calculations show that even microscopic wormholes would require negative energy equivalent to stellar masses. More fundamentally, traversable wormholes might violate causality, allowing time travel paradoxes. The universe seems to forbid shortcuts just as strictly as it forbids exceeding light speed directly. The cosmic speed limit might be connected to the nature of time itself. Some physicists propose that time emerges from entanglement between quantum systems. In this view, the speed of light represents the maximum rate at which quantum correlations can propagate, defining the flow of time. Exceeding light speed wouldn't just be impossible, it would be meaningless, like asking what's north of the North Pole. Observations of distant supernovae revealed that the universe's expansion is accelerating. Dark energy, whatever it is, pushes space apart faster and faster. Galaxies beyond a certain distance are already receding faster than light, not because they're moving through space that fast, but because space itself expands between us. This cosmic acceleration means that even at light speed, we could never reach most of the observable universe. The speed limit combines with cosmic expansion to trap us in an ever-shrinking bubble of accessibility. The fundamental structure of space-time itself rebels against light-speed travel. Einstein's field equations show that space-time is not a passive stage, but an active participant in physics. As objects accelerate, they create gravitational waves, ripples in space-time that carry energy away. The LIGO and Virgo observatories have detected these waves from merging black holes, confirming that acceleration has a cosmic cost. At near light speeds, the energy lost to gravitational radiation would become significant, creating yet another barrier to reaching C. Recent breakthroughs in understanding quantum gravity hint at why light speed is inviolable. Loop quantum gravity suggests space-time is woven from tiny loops at the Planck scale, 10 to the negative 35 meters. These loops can only change state at a finite rate, potentially explaining why information and causality are limited to light speed. If space-time is fundamentally discrete, then light speed might represent the maximum rate at which the universe can update its own state. The phenomenon of Hawking radiation provides another perspective on the speed limit. Black holes evaporate by emitting particles, with smaller black holes radiating faster. As we approach light speed, the Unruh effect suggests we would observe similar radiation. Some theorists propose that at light speed itself, this radiation would become infinite, creating a thermal barrier that no material object could survive. The universe might enforce its speed limit through a wall of quantum fire. Let me share what we've learned from the most extreme objects in the universe. Magnetars, neutron stars with magnetic fields a quadrillion times stronger than Earth's, accelerate particles to near light speeds. These cosmic accelerators show us that even with the strongest forces in nature, reaching true light speed remains impossible. Particles spiral along magnetic field lines, radiating energy and naturally limiting their velocity. Nature's most powerful engine still can't break the cosmic speed limit. The connection between light speed and causality runs deeper than most realize. In special relativity, events separated by space-like intervals have no definite time order. Different observers disagree about which happened first. If we could travel faster than light, we could visit events in our past light cone, potentially changing history. The universe seems to forbid light-speed travel specifically to prevent these causality violations. The speed limit isn't arbitrary, it's the universe protecting its own logical consistency. Quantum field theory reveals that particles are excitations in underlying fields. Photons are ripples in the electromagnetic field that naturally propagate at C because they have no mass. Massive particles are excitations in other fields that interact with the Higgs field, giving them mass and preventing light-speed travel. The Large Hadron Collider's discovery of the Higgs boson confirmed this mechanism. Mass itself might be nature's way of enforcing the speed limit on most particles. The cosmological horizon presents the ultimate futility of approaching light speed. Due to dark energy's acceleration of cosmic expansion, galaxies beyond about 16 billion light-years are receding faster than light. Even if we could travel at light speed, we could never reach them. The observable universe shrinks every moment, with galaxies crossing the horizon and becoming forever unreachable. Speed isn't fast enough to explore most of the universe, a cosmic irony that makes our limitation even more profound. Recent studies of time crystals, structures that repeat in time rather than space, suggest new ways of understanding temporal limitations. These quantum systems exhibit perpetual motion without violating thermodynamics by existing in their lowest energy state. Some physicists speculate that the light speed limit might be related to similar temporal symmetries. Just as crystals have maximum propagation speeds for vibrations, space-time might have a maximum propagation speed for causality. The measurement problem in quantum mechanics adds another layer to light speed impossibility. When we measure a quantum system, its wave function appears to collapse instantaneously. This seems to violate relativity, but careful analysis shows no information travels faster than light during measurement. The universe maintains its speed limit even during the most mysterious quantum processes. Recent experiments with quantum erasers and delayed choice confirm that causality never truly breaks, even when quantum effects seem instantaneous. Let's examine how different fundamental forces respect the speed limit. The electromagnetic force is mediated by photons traveling at c. The strong and weak nuclear forces use massive bosons that travel slower than light. Gravity propagates via waves at exactly light speed, as confirmed by simultaneous detection of gravitational waves and light from neutron star mergers. Every fundamental interaction respects the cosmic speed limit, suggesting it's woven into the fabric of physics itself. The anthropic principle offers a philosophical perspective on why light speed must be finite and unreachable. If light speed were infinite, electromagnetic forces would propagate instantaneously, making stable atoms impossible. If it were easily reachable, time dilation and causality violations would make complex structures like life impossible. We exist in a universe with this specific speed limit because universes with different limits might not support observers to wonder about them. Plasma physics at extreme conditions reveals practical barriers to light-speed travel. The solar wind accelerates particles to hundreds of kilometers per second, creating a hostile environment for spacecraft. At relativistic speeds, even this thin plasma would become a dense wall of particles. The Voyager spacecraft, now in interstellar space, measures the interstellar medium's density. Calculations show that at near-light speed, impacts with this sparse matter would deliver energy comparable to nuclear explosions. The false vacuum hypothesis suggests our universe might not be in its lowest energy state. If true, the vacuum could decay, spreading at light speed and destroying everything. Some physicists speculate that attempting to reach light speed might trigger local vacuum decay. The energy densities required might destabilize the Higgs field, creating a bubble of true vacuum that expands at c, annihilating everything in its path. The universe's speed limit might protect against existential catastrophe. String theory, our best candidate for quantum gravity, predicts extra dimensions beyond the familiar four. These dimensions might be compact, curled up at every point in space. Movement through regular space might involve complex trajectories through these hidden dimensions. Light speed could represent a fundamental limitation on how fast information can navigate this higher dimensional manifold. What seems like a speed limit might be a geometric constraint in dimensions we can't perceive. The engineering challenges of even approaching light speed reveal the absurdity of reaching it. Consider the most optimistic scenario: a perfect antimatter rocket with 100% efficiency. When matter and antimatter annihilate, they convert entirely to energy, the maximum possible by Einstein's equation. Yet even this perfect engine would need tons of antimatter to accelerate a small probe to 90% light speed. We currently produce antimatter in quantities measured in individual atoms, at costs exceeding trillions of dollars per gram. CERN's antiproton decelerator, the world's premier antimatter factory, produces about 10 nanograms of antiprotons annually. At this rate, creating enough antimatter for one relativistic journey would take longer than the current age of the universe. Even if we revolutionize production by factors of millions, the energy required to create antimatter exceeds what it releases. The universe seems to mock our ambitions with thermodynamic impossibilities. Recent experiments with laser propulsion offer a glimpse of the challenges ahead. Breakthrough. Starshot proposes using powerful lasers to push tiny light sails to 20% light speed. But calculations show the laser array would need to generate 100 gigawatts, the output of 100 large power plants, focused perfectly on meter-wide sails thousands of kilometers away. Any imperfection would vaporize the sail instantly, and this is for grain-sized payloads reaching just 1/5 light speed. The materials science requirements for relativistic travel border on fantasy. At 90% light speed, a spacecraft hull would need to withstand impacts with interstellar dust grains, carrying kinetic energy comparable to bullets. Current materials would vaporize instantly. Theoretical solutions like electromagnetic shields would themselves require enormous energy, adding mass that makes acceleration even harder. We're caught in an engineering spiral where every solution creates new problems. Let's talk about the navigation impossibility at near-light speeds. Due to relativistic aberration, stars ahead would crowd into a brilliant circle, while everything behind fades to black. The cosmic microwave background would blue shift into blinding gamma radiation in front and red shift to invisibility behind. Pilots would be effectively blind, unable to see their destination or correct their course. The faster you go, the narrower your view becomes, until at light speed itself, the entire universe would compress to a single, infinite point of light ahead. The Penrose-Terrell rotation effect adds another visual distortion. Objects don't just length contract at relativistic speeds, they appear to rotate. A cube passing by at near light speed would seem to twist, showing faces that should be hidden. This isn't an optical illusion, but a real consequence of light travel time from different parts of the object. Navigation computers would need to account for these distortions, reconstructing actual positions from wildly warped observations. Communication with relativistic spacecraft presents insurmountable challenges. Signals from a ship traveling at 99% light speed would be red-shifted by factors of 14. Radio waves would stretch into unusably low frequencies. Worse, time dilation means the crew experiences time 7 times slower than Earth. A conversation would take decades, with questions and answers separated by lifetimes. By the time Earth received trip reports, civilizations might have risen and fallen. The Rindler horizon demonstrates another barrier to light-speed travel. A constantly accelerating observer experiences an event horizon behind them, a boundary beyond which no signal can catch up. As acceleration approaches what would be needed for light speed, this horizon creeps forward, eventually cutting the traveler off from the entire universe. At light speed, the horizon would surround them completely, trapping them in a bubble, disconnected from all reality. Recent discoveries about dark matter add mysterious complications. We know dark matter interacts gravitationally but seems invisible to electromagnetic forces. At relativistic speeds, would dark matter present a barrier? Would its gravitational effects become significant? The bullet cluster observations show dark matter and regular matter can separate during cosmic collisions. A relativistic spacecraft might experience unprecedented interactions with this invisible mass filling the galaxy. The quantum Zeno effect suggests that frequent observation can freeze a quantum system's evolution. Some theorists speculate that at relativistic speeds, interaction with the quantum vacuum might create a similar effect, freezing the traveler's ability to accelerate further. The universe might continuously observe near-light-speed objects through vacuum interactions, preventing them from reaching C through quantum mechanical prohibition. Experimental evidence from cosmic ray physics reinforces the barrier. The Oh My God particle, detected in 1991, was a proton with energy equivalent to a baseball thrown at 60 miles per hour, compressed into a single subatomic particle. The GZK cutoff provides natural evidence of relativistic limits. Ultra-high-energy cosmic rays should lose energy through interactions with the cosmic microwave background, creating a maximum energy for particles reaching Earth from distant sources. The fact we observe this cutoff confirms that even cosmic accelerators, billions of times more powerful than anything humans could build, still can't overcome the universal speed limit. Time travel paradoxes reveal why the universe must forbid light-speed travel. The tachyonic anti-telephone thought experiment shows that faster-than-light communication would allow sending messages into the past, creating causality loops. You could receive a reply before sending the question, or prevent yourself from sending the message that caused the reply. The universe seems to enforce the speed limit specifically to prevent these logical contradictions that would unravel cause and effect. Recent advances in metamaterials have created substances with negative refractive indices, seemingly allowing faster-than-light phase velocities, but careful analysis shows that no information or energy actually exceeds c. The peaks of waves might race ahead, but the signal itself, the part carrying information, still respects the speed limit. Even when we engineer materials with exotic properties, the universe finds ways to preserve its fundamental restrictions. The concept of rapidity in special relativity offers another perspective. While velocity is limited to c, rapidity can increase without bound. It's the hyperbolic angle in space-time, and unlike velocity, rapidities add linearly. But infinite rapidity still only corresponds to light speed. The universe has built its speed limit into the very geometry of space-time. No amount of mathematical transformation can break this geometric barrier. The economics of approaching light speed presents a reality check that transcends physics. Even if we solved every technical challenge, the energy costs a civilization ending. Accelerating 1 kilogram to half light speed requires energy equivalent to the entire United States power output for months. Scale that to a crewed spacecraft massing thousands of tons, and you need energy exceeding global consumption for centuries. The universe prices light speed travel beyond any conceivable economy. Neutrino physics offers fascinating insights into the speed barrier. These ghostly particles have tiny but non-zero mass, forcing them to travel slightly slower than light. The Super Kamiokande detector in Japan and IceCube at the South Pole have measured neutrinos from supernovae arriving hours after the light from the same events. If particles with almost no mass can't reach light speed, it demonstrates how absolute the prohibition is for anything with substantial mass. The quantum vacuum isn't empty but seethes with virtual particles appearing and disappearing. At relativistic speeds, these quantum fluctuations become a serious problem. The dynamic Casimir effect predicts that accelerating mirrors can convert virtual photons into real ones. A spacecraft approaching light speed would face an ever-intensifying storm of particles materialized from the vacuum itself. The empty space between stars would become a blazing inferno of radiation created by your own motion. Recent observations of fast radio bursts provide natural experiments in extreme physics. These millisecond pulses travel billions of light years, allowing us to test whether different frequencies of light travel at slightly different speeds. So far, measurements confirm that all electromagnetic radiation travels at exactly c, regardless of energy. This universality suggests the speed limit is fundamental to space-time itself, not just a property of light. The binding energy of matter reveals another barrier. As objects approach light speed, the energy holding their atoms together becomes negligible compared to their kinetic energy. Calculations suggest that at sufficient velocity, electromagnetic bonds would simply fail. Atoms would dissociate into plasma, molecules would shatter, and any organized structure would dissolve into a cloud of particles. The universe might enforce its speed limit by destroying anything that tries to break it. Let's examine what we've learned from ultra-precise atomic clocks. Researchers at NIST have created clocks so accurate they won't gain or lose a second in 30 billion years. These clocks can detect time dilation from walking speed velocities. They've shown that climbing a single stair step makes time pass faster due to reduced gravity. If such tiny changes in velocity and gravity create measurable effects, the distortions at near-light speed would be overwhelming. The phenomenon of pair production adds another barrier. When photons with sufficient energy interact with matter, they can create particle-antiparticle pairs. At relativistic speeds, even low-energy photons blue shift enough to trigger this process. A near-light-speed spacecraft would be surrounded by a cloud of electrons and positrons created from its interaction with starlight. This cascade of particle creation would drain energy and create a drag force opposing acceleration. Black hole physics provides the ultimate example of light speed's inviolability. At the event horizon, escape velocity equals c. Nothing, not even light, can escape from within. The existence of black holes proves that light speed is truly a maximum. If anything could exceed it, black holes couldn't exist. LIGO's detection of merging black holes confirms their reality, and thus the absoluteness of the cosmic speed limit. The information paradox in black holes connects to light speed limitations in unexpected ways. Stephen Hawking showed that black holes evaporate through quantum radiation, potentially destroying information that falls in. Recent theories suggest information might be preserved on the event horizon or released in highly scrambled form. This deep connection between information, gravity, and light speed hints that the speed limit might be fundamentally about information preservation. Studies of superfluids and Bose-Einstein condensates reveal how quantum mechanics enforces speed limits. In these exotic states of matter, atoms lose individual identity and behave as single quantum objects. Sound waves in superfluids have maximum velocities determined by quantum properties. Some physicists speculate that space-time itself might be a kind of superfluid, with light speed representing its fundamental sound velocity, the speed at which disturbances propagate. The covariant formulation of electromagnetism shows why light speed is special. Maxwell's equations naturally predict electromagnetic waves traveling at c. This isn't coincidence but necessity. The speed emerges from the fundamental relationship between electric and magnetic fields. Changing light speed would require rewriting electromagnetism, which would alter atomic structure, chemistry, and ultimately make our form of life impossible. Recent experiments with quantum teleportation might seem to violate light speed limits, but they actually confirm them. While quantum states can be transferred instantly through entanglement, the process requires classical communication at light speed to complete. The universe allows instant correlations, but carefully prevents faster-than-light information transfer. It's as if nature permits spooky connections while jealously guarding causality. The concept of proper time reveals the deepest reason for light speed limits. Every object travels through space-time at exactly c. Massive objects mostly through time, photons entirely through space. As you accelerate through space, you must travel less through time to maintain this constant space-time velocity. At light speed, all motion would be through space with no passage through time. This geometric truth makes light speed unreachable for anything experiencing time. Observations of blazars, supermassive black holes shooting jets at near-light speeds, show natural acceleration limits. These cosmic particle accelerators, powered by gravity and magnetic fields billions of times stronger than Earth's, still can't push particles to true light speed. The jets achieve 99.9% of c, but never higher, confirming that even the universe's most extreme engines respect the ultimate barrier. The holographic principle suggests information in any region is proportional to surface area, not volume. This implies fundamental limits on information density and processing speed. Some theorists propose that light speed represents the maximum rate at which information can flow across these holographic boundaries. Exceeding it would require infinite information density, creating paradoxes that space-time resolves by forbidding light speed travel. The discovery of gravitational waves has given us a new window into light speed limitations. When LIGO detected the first merger of black holes in 2015, the waves arrived exactly when expected if gravity travels at c. The 2017 neutron-star merger was even more revealing. Gravitational waves and light from the same event arrived within seconds after traveling 130 million light-years. This confirms that the universe's speed limit applies to space-time itself, not just matter and energy moving through it. Quantum entanglement experiments continue to probe the boundaries of light speed limits. Scientists at the University of Science and Technology of China have demonstrated entanglement between satellites and ground stations thousands of kilometers apart. While correlations appear instantaneous, careful analysis shows that no usable information exceeds light speed. The universe seems to have built elaborate safeguards to allow quantum weirdness while preserving relativistic causality. The Parker Solar Probe, humanity's fastest spacecraft, offers real-world lessons in relativistic challenges. Reaching speeds of 195 kilometers per second required a complex trajectory using multiple Venus flybys. Even this tiny fraction of light speed required years of gravitational assists. To reach just 1% of C would require gravity assists from objects that don't exist in our solar system. The engineering reality falls absurdly short of science fiction dreams. Let me explain how the expansion of space itself creates an ultimate futility to light speed travel. Space between galaxy clusters expands at about 70 kilometers per second per megaparsec. Galaxies sufficiently distant are already receding faster than light, not through space, but because space itself stretches. Even if we could travel at light speed, most of the universe would remain forever unreachable. The cosmos has built a cage of expanding space-time that no speed can overcome. The symplectic structure of phase space in physics reveals deep mathematical reasons for the speed limit. In Hamiltonian mechanics, the evolution of any system preserves certain geometric properties. Light speed emerges as the maximum rate at which information can flow while preserving these structures. Exceeding it would break the mathematical framework that allows prediction and causality. The universe's speed limit might be geometry itself refusing to be violated. Recent studies of pulsar timing arrays have placed incredibly stringent limits on any variation in fundamental constants, including light speed. The nanograv collaboration uses millisecond pulsars as cosmic clocks, timing their pulses to nanosecond precision over years. Any change in C would alter these rhythms detectably. After decades of observation, we've found no variation, confirming that light speed has remained constant for billions of years across vast cosmic distances. The quantum Hall effect demonstrates how fundamental constants conspire to enforce limits. In two-dimensional electron systems at low temperatures and high magnetic fields, electrical resistance becomes quantized in units involving light speed, Planck's constant, and electron charge. These quantum states are so robust that they're used to define electrical standards. The deep connection between electromagnetism and light speed appears even in exotic quantum phases of matter. Acoustic black holes created in laboratory fluids provide analog systems for studying horizons. Scientists have created regions where fluid flow exceeds sound speed, trapping sound waves like black holes trap light. These experiments confirm that horizons and speed limits are generic features of wave propagation, not specific to light. The mathematics that prevents exceeding sound speed in fluids is identical to what prevents exceeding light speed in spacetime. The possibility of closed time-like curves in general relativity reveals why light speed must be limited. Solutions like the Gödel universe or rotating black holes theoretically allow paths through space-time that return to their starting point in both space and time. But these require either infinite rotation speeds or faster-than-light travel. The universe seems to forbid light speed travel specifically to prevent these time loops that would destroy causality and free will. Consider what we've learned from the most precisely measured phenomenon in physics, the magnetic moment of the electron. Quantum electrodynamics predicts this value to 12 decimal places confirmed by experiment. This extraordinary agreement between theory and measurement depends critically on light speed being exactly what it is. Change c even slightly, and the entire theoretical framework collapses. The universe's constants aren't arbitrary, they're interlocked in ways that make light speed unchangeable. The concept of chronology protection, proposed by Stephen Hawking, suggests the universe actively prevents time travel paradoxes. Whenever general relativity seems to allow faster-than-light travel or time machines, quantum effects intervene to destroy them. Virtual particles would circulate through any would-be time machine, building to infinite energy and destroying the device. The universe might enforce its speed limit through quantum mechanical censorship of causality violations. Studies of ultra-high-energy cosmic rays reveal another facet of the speed barrier. The Pierre Auger Observatory detects particles with energies exceeding 10 to the 20th electron volts. At these energies, protons experience extreme time dilation. Their journey across the galaxy takes moments from their perspective. Yet even these highest energy particles in the universe still fall infinitesimally short of light speed. Nature's most violent events can't break the cosmic speed limit. The relationship between entropy and information provides thermodynamic reasons for light speed limits. Information has physical properties. It requires energy to create or destroy and increases entropy when erased. The Landauer principle sets minimum energy costs for information processing. At light speed, information processing would require infinite energy, making computation impossible. The universe might limit speed to preserve the possibility of information and consciousness. Recent discoveries about axions, hypothetical dark matter particles, suggest new perspectives on speed limits. If axions exist, they would oscillate at frequencies determined by their mass and couple extremely weakly to light. Some theories propose that what we call empty space is filled with an axion field that sets the cosmic speed limit. Light speed might not be fundamental, but emergent from deeper fields we're only beginning to discover. The cosmic censorship hypothesis proposes that singularities must be hidden behind event horizons. Naked singularities, points of infinite density visible to outside observers, would break physics. Since event horizons form where escape velocity equals light speed, the cosmic speed limit might exist to hide the universe's mathematical infinities. Without this limit, singularities would be exposed, potentially unraveling space-time itself. The phenomenon of Cherenkov radiation provides a beautiful demonstration of light speed's role in nature. When charged particles travel through a medium faster than light speed in that medium, not faster than c in vacuum, they create a blue glow. Nuclear reactors shimmer with this ethereal light as particles exceed light's reduced speed in water. This effect proves that while local phase velocities can vary, the vacuum speed of light remains the absolute universal maximum that nothing can surpass. Recent experiments with attosecond lasers have allowed scientists to observe electrons moving within atoms. These pulses, lasting just quintillionths of a second, reveal quantum mechanics at its most fundamental scale. Even at these tiniest distances and shortest times, nothing exceeds light speed. Electrons tunnel through barriers seemingly instantaneously, but careful measurement shows the process still respects relativistic limits. The universe enforces its speed limit down to the smallest observable scales. The cosmic web structure provides large-scale evidence of light speed limitations. Galaxy clusters connected by dark matter filaments evolved over billions of years, with gravity propagating at c between massive objects. Computer simulations like the Millennium simulation must account for light speed delays in gravitational interactions. If gravity traveled faster than light, the universe's large-scale structure would look completely different. Every galaxy cluster's position confirms that nothing, not even gravity itself, exceeds the cosmic speed limit. Let's discuss how quantum chromodynamics, the theory of the strong force, relates to light speed limits. Inside protons and neutrons, quarks and gluons interact at speeds approaching c. The RHIC experiments at Brookhaven have created quark-gluon plasma by colliding gold nuclei at 99.95% light speed. This recreates conditions from microseconds after the Big Bang. Even in this extreme state, with temperatures exceeding 4 trillion degrees, particles still can't reach true light speed. The discovery of time dilation in GPS satellites has practical implications most people never consider. Without relativistic corrections, GPS errors would accumulate at 10 kilometers per day. Your smartphone performs Einstein's calculations thousands of times per second. This isn't abstract physics, it's engineering necessity. If we can barely handle relativistic effects at orbital speeds of 4 kilometers per second, imagine the impossibility of managing them near light speed. Studies of binary pulsars provide natural laboratories for testing relativistic limits. The Hulse-Taylor binary, discovered in 1974, consists of two neutron stars orbiting each other at speeds reaching 2,000 kilometers per second. Their orbit decays exactly as general relativity predicts, losing energy to gravitational waves. After decades of observation, the measured orbital decay matches theory to better than 0.2%. These cosmic laboratories confirm that nature itself can't break the rules we've discovered. The concept of the Planck scale reveals potentially fundamental reasons for light speed limits. At distances of 10 to the negative 35 meters and times of 10 to the negative 43 seconds, quantum mechanics and general relativity collide. Some theories suggest space-time itself becomes discrete at this scale, like pixels on a screen. Light speed might represent the maximum rate at which these pixels can update, a cosmic refresh rate built into reality's operating system. Recent observations of kilonovae, collisions between neutron stars, have revealed where heavy elements like gold and platinum originate. The LIGO detection of GW17817, followed by optical observations, showed that these collisions accelerate matter to significant fractions of light speed. Yet even these cosmic forges, powered by gravity so strong that atomic nuclei touch, can't achieve true light speed. The universe's most violent events still respect its ultimate rule. The vacuum birefringence predicted by quantum electrodynamics has recently been observed around neutron stars. In extreme magnetic fields, the vacuum itself becomes polarized, affecting light propagation. This shows that even empty space has structure that depends on light speed. Change c and you change the vacuum itself. The universe's speed limit isn't just about moving through space, it's woven into space's fundamental properties. Quantum computing research reveals information-theoretic limits related to light speed. Quantum gates, the basic operations in quantum computers, have minimum operation times set by uncertainty principles. The fastest possible quantum computation is limited by the time light takes to cross the computer. IBM's quantum processors must account for signal propagation delays even across their tiny superconducting circuits. The universe limits not just motion, but computation itself. The firewall paradox in black hole physics suggests connections between light speed and quantum information. If information can't be destroyed, what happens when it falls into a black hole? Recent theories propose that information is encoded on the event horizon, the surface where escape velocity equals c. The light speed barrier might exist to preserve information, preventing paradoxes that would arise if information could escape black holes or be truly destroyed. Studies of meteor impacts reveal what happens when ordinary matter approaches even modest fractions of light speed. The Chicxulub impact that killed the dinosaurs involved an asteroid hitting Earth at about 20 kilometers per second. just 0.007% of c. This released energy equivalent to billions of nuclear bombs. Scale this to relativistic speeds, and a grain of sand would deliver city-destroying energy. The universe makes high-speed travel apocalyptically dangerous. The false vacuum theory suggests our universe might exist in a metastable state. If the Higgs field could transition to a lower energy state, the change would propagate at light speed, destroying everything. Some physicists speculate that attempting to reach light speed might trigger such a transition locally. The universe's speed limit might protect against accidentally destroying reality itself through excessive acceleration. Observations of active galactic nuclei show natural particle accelerators at work. Supermassive black holes launch jets extending millions of light-years, accelerating particles to 99.9% of c. The Event Horizon Telescope's image of M87's black hole shows these jets in action. Despite magnetic fields billions of times stronger than Earth's and gravitational forces that shred stars, these cosmic accelerators still can't achieve true light speed. The concept of tachyon condensation in string theory suggests why faster-than-light particles can't exist. If tachyons were real, they would cause the vacuum to become unstable, rapidly condensing into a lower energy state. The absence of tachyons isn't just observational, it might be necessary for the universe's stability. Light speed isn't just a maximum, it's a boundary between existence and impossibility. The connection between consciousness and light speed opens profound philosophical questions. Some interpretations of quantum mechanics suggest consciousness plays a role in wave function collapse. If observation requires conscious awareness, and information about observations can't travel faster than light, then consciousness itself might be fundamentally limited by c. We might not just be unable to travel at light speed, our very thoughts and awareness might exist because of this limitation. Recent discoveries about the quantum Zeno effect show how observation affects reality at fundamental levels. By continuously measuring a quantum system, we can freeze its evolution. At relativistic speeds, interaction with the quantum vacuum might create a similar effect, with the universe constantly observing fast-moving objects. This cosmic surveillance might create increasing resistance as objects approach c, making the final push to light speed require infinite observations and infinite energy. The ADS-CFT correspondence, one of the most profound discoveries in theoretical physics, suggests our three-dimensional universe might be a projection from a two-dimensional boundary. In this holographic view, the speed of light represents the maximum rate at which information can propagate from the boundary to the bulk. Exceeding light speed would be like a movie trying to play faster than its film can move through the projector, physically meaningless in the deepest sense. Let me share what we've learned from the most extreme laboratory conditions ever created. The relativistic heavy ion collider has achieved temperatures of 4 trillion degrees Celsius, 250,000 times hotter than the Sun's core. In these conditions, protons and neutrons melt into quark-gluon plasma. Yet even in this primordial soup, where matter barely exists as we know it, particles still can't exceed light speed. The limit holds even when matter itself breaks down. The delayed choice quantum eraser experiment reveals how light speed affects causality in quantum mechanics. By choosing whether to measure certain properties after photons have already been detected, we seem to change the past. But careful analysis shows no information travels backward in time or faster than light. The universe has constructed quantum mechanics to allow seemingly impossible correlations while preserving the causal structure that light speed enforces. Observations of millisecond pulsars, neutron stars spinning hundreds of times per second, provide natural tests of extreme physics. The surface of these objects moves at significant fractions of c. Any faster and they would fly apart from centrifugal force. The fastest observed pulsar, PSRJ, 1748-2446, rotates 716 times per second. Its equator travels at about 24% light speed, nature pushing against the cosmic speed limit. The information loss paradox in black holes connects to fundamental questions about light speed and reality. If information falling into black holes is truly destroyed, it would violate quantum mechanics. But if it's preserved, how does it escape when nothing can exceed light speed? Recent theories suggest information might be encoded in subtle correlations in Hawking radiation, released at exactly c. The universe's speed limit might be essential for information conservation. Studies of cosmic voids, vast empty regions between galaxy clusters, reveal how even nothingness respects light speed. These voids expand as dark energy pushes space apart, but the expansion information propagates at c. We can watch voids grow in real time, cosmologically speaking, by observing how light from distant galaxies bends around them. Even emptiness can't communicate faster than light. The quantum speed limit, also called the Margolis-Levitin theorem, sets a fundamental maximum rate for quantum state changes. No quantum system can evolve from one distinguishable state to another faster than a time set by its energy and Planck's constant. This isn't just about motion through space, but about change itself. The universe has a maximum rate of transformation, and light speed is its manifestation in space-time. Recent experiments with Bose-Einstein condensates have created analogues of expanding universes in laboratory settings. By controlling how sound propagates through these ultra-cold atomic clouds, scientists simulate cosmic inflation and even black hole horizons. These toy universes confirm that speed limits are generic features of any system with wave propagation. Light speed isn't unique to our universe but might be inevitable in any reality with causality. The phenomenon of vacuum decay illustrates ultimate consequences of the speed limit. If our universe's vacuum is metastable, a bubble of true vacuum would expand at exactly light speed, annihilating everything. This doomsday scenario can't propagate faster than c, giving distant regions time to exist before destruction arrives. Paradoxically, the speed limit that prevents us from escaping also prevents instant cosmic catastrophe. Gamma-ray astronomy reveals the universe's highest energy phenomena still respect light speed. The Hess telescopes detect photons with energies exceeding 10 trillion electron volts from distant blazars. These photons have traveled billions of years without exceeding c, despite carrying energy densities that would vaporize anything they hit. Even pure energy in its most extreme form can't break the cosmic speed limit. The relationship between complexity and light speed suggests deep connections. Complex systems require time for information to propagate between components. At light speed, time dilation becomes infinite, freezing any process. Complexity, computation, life, and consciousness might exist only because light speed is finite and unreachable. The universe's speed limit might be the prerequisite for interesting things to happen. Studies of neutron star mergers have revealed where many elements heavier than iron originate. The kilonova AT 2017 GeHeFo showed matter ejected at 30% light speed, creating rapid neutron capture conditions that forge gold, platinum, and uranium. Even these cosmic element factories, powered by the strongest gravity outside black holes, can't achieve speeds that would make the nuclear physics fail. The periodic table exists because nothing can reach light speed. The cosmic neutrino background, relic neutrinos from 1 second after the Big Bang, provides evidence that light speed has remained constant for nearly 14 billion years. These ghostly particles, though never directly detected, must exist based on Big Bang nucleosynthesis. Their influence on cosmic structure formation depends critically on them traveling just below C. If light speed had varied, the universe's large-scale structure would be different. As we reach the end of this cosmic journey through the impossibility of light-speed travel, let's confront the profound truth. The universe's speed limit isn't a flaw to be overcome, but a feature that makes existence possible. Without this cosmic constraint, atoms couldn't form, stars couldn't shine, and the delicate dance of forces that allows life would collapse into chaos. We exist not despite the speed limit, but because of it. The accumulated evidence from every corner of physics, from particle accelerators to pulsars, from GPS satellites to gravitational waves, points to an inescapable conclusion. Light speed isn't just difficult to reach, it's woven into the fundamental structure of reality. Mass, energy, space, time, and causality all interconnect through this cosmic constant. Trying to exceed it would be like trying to travel north from the North Pole. Not just impossible, but conceptually meaningless. Consider what we've learned from humanity's fastest achievements. After decades of engineering brilliance and billions of dollars, our fastest spacecraft reach about 0.06% of light speed. The Large Hadron Collider, representing the pinnacle of human technology, accelerates protons to 99.9% of c and requires the energy output of a small city to do so. Each additional 9 in that percentage requires exponentially more energy, approaching infinity as we near the ultimate barrier. The philosophical implications stretch beyond mere physics. We are beings made of matter that arose from energy, following patterns dictated by the speed of light. Every atom in your body, forged in stellar cores and supernova explosions, exists because nuclear reactions proceed at rates governed by c. Your thoughts, traveling as electrical impulses through neurons, are ultimately limited by the same cosmic speed that limits the stars. We are not separate from the universe's rules, we are manifestations of them. Recent observations continue to reinforce the absolute nature of this limit. The Event Horizon Telescope's image of black holes, LIGO's detection of colliding neutron stars, the James Webb Space Telescope's views of the earliest galaxies, all confirm that light speed has remained constant across billions of years and billions of light years. If this fundamental constant could change or be exceeded, we would see evidence in these cosmic laboratories. Instead, we find perfect consistency. But here's the beautiful paradox: the very limit that confines us also connects us to the cosmos. When you look at stars, you're seeing them as they were years ago, their light having traveled at exactly c to reach your eyes. This finite speed makes the universe a time machine, allowing us to witness cosmic history directly. If light traveled instantaneously, we would lose this connection to the past, this ability to see the universe's evolution written in the night sky. The search for loopholes continues, and it should. Science progresses by questioning limits and testing boundaries. Alcubierre drives, wormholes, and other exotic solutions to Einstein's equations tantalize us with possibilities. But each requires conditions that may be impossible: negative energy densities, exotic matter, or modifications to general relativity that observations don't support. The universe seems to have closed every door, sealed every loophole, and built the speed limit into reality's bedrock. Let me share a perspective that transforms disappointment into wonder. Yes, we'll never travel at light speed, but photons do, and we are intimately connected to them. Every second, trillions of photons that have traveled at c since the Big Bang pass through your body. You are continuously bathed in light that has experienced no time, from its perspective having crossed the universe instantaneously. In a sense, you are constantly touching something that does what we cannot: travel at the cosmic speed limit. The anthropic principle offers a final insight. We observe a universe with this specific speed limit because universes with different limits might not support observers. If c were infinite, electromagnetic forces would propagate instantaneously, making stable atoms impossible. If c were achievable by massive objects, time dilation and causality violations would prevent complex structures from forming. We exist in a Goldilocks universe where the speed of light is just right for consciousness to emerge and ponder its own limitations. As technology advances, we'll continue pushing against this barrier, and we should. Each attempt teaches us more about the universe's structure. Breakthrough starshot might send tiny probes at 20% light speed to nearby stars. Future antimatter rockets might achieve higher fractions, but the exponential curve of energy requirements ensures we'll always fall short of true light speed, always remain time-bound travelers in a universe larger than we can ever fully explore. This limitation shapes humanity's cosmic future. We'll never have Star Trek's warp drive or Star Wars hyperspace. Interstellar civilization, if it happens, will involve generation ships traveling for centuries, colonies separated by years of communication delay, and human species diverging through isolation. The universe's speed limit doesn't just constrain our technology, it will fundamentally shape what humanity becomes among the stars. Yet understanding why we can't reach light speed reveals something profound about our place in the cosmos. We are not prisoners trapped by an arbitrary rule, but participants in a universe whose very consistency allows us to exist. The same limit that prevents us from reaching distant stars also prevents causality from unraveling, keeps atoms stable, and maintains the flow of time that makes experience possible. Think about what this means for your daily existence. Every morning when sunlight reaches your window, it has traveled 8 minutes at exactly Ta'i from our star. The warmth you feel obeys the same relativistic rules that prevent interstellar travel. Your GPS navigation works because engineers account for time dilation. The computer or phone you're using exists because quantum mechanics respects light speed. We live surrounded by evidence of the cosmic speed limit, benefiting from its consistency even as we dream of exceeding it. The universe has written its speed limit not in some cosmic law book but into the fabric of existence itself. From the quantum foam at the Planck scale to the expansion of space itself, from the dance of electrons around atoms to the collision of galaxy clusters, everything respects this ultimate boundary. It's not a wall we might someday break through, but the foundation upon which reality stands. As you contemplate these cosmic constraints, remember that understanding our limits is a form of transcendence. We are the only known beings who can comprehend why we can't travel at light speed, who can work out the equations that bind us, who can dream of impossible journeys while understanding precisely why they're impossible. In our knowledge of the barrier, we achieve a different kind of cosmic travel, not through space but through understanding. So tonight, when you look up at the stars, see them differently. Those points of light aren't destinations you'll never reach, but messengers traveling at the only speed the universe allows, carrying stories across the cosmic gulf. You'll never travel at light speed, but you're built from particles that have danced with photons for billions of years. You think with a brain that processes reality at speeds ultimately limited by c, and you exist because the universe has this precise, unbreakable rule. We are light-bound creatures in a light-speed-limited universe, and that's not a tragedy. It's the foundation of everything beautiful, complex, and meaningful in existence. The cosmic speed limit isn't what keeps us from the stars, it's what allows us to exist, to dream of them in the first place. And in that knowledge, in that deep understanding of our place in the cosmic order, we find not limitation, but connection to the grand story of a universe that makes sense, follows rules, and allows conscious beings to discover and marvel at its constraints. The speed of light will forever remain beyond our reach, and in that eternal impossibility lies the very possibility of our existence. We cannot break the cosmic speed limit, but in understanding why, we touch something even more profound: the deep structure of reality itself, the mathematical poetry that governs existence, and our own remarkable ability to comprehend the incomprehensible. That's the true magic, not traveling at light speed, but understanding why we never will and finding wonder in that limitation itself. If you are still watching, make sure to subscribe to the channel and give a thumbs up. Your support is my biggest fuel to keep motivated. And if you enjoyed this video, I am sure you will love this other one at the left side of the screen. How was the speed of light measured? In this video, we reveal the incredible story of how humanity unlocked one of the universe's most fundamental constants. From Galileo's lantern experiments and Romer's observations of Jupiter's moons, to Fizeau's spinning wheels, Foucault's rotating mirrors, and the legendary Michelson-Morley experiment. See you there.